Well, so welcome you all to the next session of the S.J.Sarkar's Basic Electrical Engineering lectures. So we had discussed a lot about DC network theorem. Now coming towards the AC circuits, let us try to understand that how we could solve the problem associated with this AC circuit in a very simpler manner. But one point I must add up over here, that in order to understand this AC system, we should have a clear conception about this vector algebra, because we would be using the polar form and Cartesian form interchangeably to solve this particular circuit. So let us suppose I am having a circuit something like this one. I am having a R and L in parallel to a C, and the entire combination is in series with the resistance R1. And the values are given that R1 equal to 100 ohm, R2 equal to 50 ohm, L equal to 150 millihenry, C is 20 mu F, and V, that is the applied voltage, that is given 282.8 sin 314t minus 15 degree. Now what we need to do, we have to find out IL and IC, means current passing through this RL and C. We have to find out what is the voltage drop across R2 and what is the voltage drop across L, and also we have to find out the active, reactive and apparent power delivered by this source V. So let's see how we are going to proceed to solve such a problem. Now what is given to you? This V is given to you. So if that V is given to you, so what we can write, that the RMS value of the voltage should be equal to the peak value. So peak value is 282.8 by root 2. So solving that, we will be getting that it would be approximately equal to 200 volt. Now what is given to you is this V is having the phase difference of minus 15 degree from the reference. So what we can write there, that the RMS of this voltage source should be represented as 200 angle minus 15 degree volt. So this is the RMS value and this is the phase angle which is given in the problem. So this is V. Now what is also known, omega is given, that is 314 radian per second. It's given there. This is the value of omega. So omega is given. Now once omega is given, so we can find out XL equal to omega L, and the value would be coming to be 47.1 ohm, and XC would be 1 by omega C, and the value would be coming to be 159.24 ohm. So we had found the reactance of this coil and reactance of this capacitor. Now we have to find out the equivalent impedance of this entire combination, this parallel combination. So let us try to find out Z, Y, Z, because this is point Y and this is point Z. So the impedance between this Y and Z will be what? That would be this RL combination will be in parallel to the C. So what is going to happen? We can write it in this way, that R2 plus JXL will be parallel to minus JXC. Now why I am writing in this way? Because what we know, that in case of this inductor, we often represent with plus J, and in case of a capacitor, we often represent it at minus JXC. So that is why I am writing in that way. Now if I am going to simplify it, the normal multiplication operation, addition operation of this complex number can be applied to have that one, because this j and complex number I, they are analogous. So if that is the case, so this zyz after solving, we would be getting that zyz is equal to 84.1 plus j 29.38 ohm. So this is in the Cartesian form. So if I am going to convert it to a polar form, it would be coming to be 89.09 angle 19.26 degree ohm. So this 89.09 what we are getting, this is the actually the impedance value, and this is showing the phase angle. Now we had found what? We had found the impedance between this y and z. Now let us suppose I am going to find out the impedance between x and z. So that would be this R1 in series with this equivalent combination. So what we can write, that would be R1 plus z yz. So solving that, what we are going to get is that should be equal to 184.1 plus j 29.38 ohm in Cartesian form. Now converting it to polar form, we are going to get 186.43 angle 9.07 degree ohm. So this value 186.43, that is basically the effective impedance of this entire combination. Now we know what is the impedance. We know what is the voltage. We had already described what is the voltage. It's known to us. So what we can write? The current I will be V by ZXZ. Now V is this one. ZXZ is either this one or this one. Any one we could take. Now simplifying them, what we are going to get is this I will be equal to 0.98 minus j 0.44 ampere, or it would be 1.073 angle minus 24.06 degree ampere. So what effectively we can call, this is the RMS value of current that is actually drawn from the supply to deliver or everything in this particular load. Now when this I is passing, so we are having some value of V1 and some value of V2. So what would be V1? That would be I into R1. So solving that, we would be coming to be 97.98 minus j 43.75 volt, or in polar form we can write it to be 107.3 angle minus 24.06 degree volt. And similarly V2 would be equal to I Z YZ, because the impedance of this region is ZYZ. So into this current I will be the V2. So solving that, this V2 will be coming to be 95.26 minus J8 volt. Now that is equal to 95.59 angle minus 4.8 degree. So this is the value of V1 and V2 we had found. Now once V2 is found, so can we write IL will be nothing but V2 by R2 plus JXL, because V2 is now known to us and the impedance of this part will be R2 plus JXL. So that is the thing. So therefore that would be the value of current. Now if we are putting all the values and simplifying it, what we are going to get is that this IL would be coming to be 0.98 minus J 0.44 ampere, which is 0.93 minus J 1.0 0.04 ampere, which is equal to 1.39 angle minus 48.09 degree ampere. So this is the RMS value of IL. So we had found this IL. Now similarly IC will be V2 by minus J XC, because the reactance of this is XC, and why minus J, because it's a capacitance there. So dividing that, what we are going to get is, this should be coming to be 0.05 plus J 0.598 ampere, which is in polar form can be given as 0.6 angle 85.2 degree. So this is basically the RMS value of IC. Now I am stopping here a bit to let you come across one interesting point. See, the RMS value of the current I is 1.073. But see the RMS value of IL, this is 1.39. It's greater than that of this 1.073. Although there is a current division there, but the RMS value of IL is coming to be more than that of IC. Now you might think that then KVL is not applicable here, but it's not true. What actually happened in this AC is that the KVL is also applicable, KCL is also applicable, but here it is not the algebraic summation. But what actually happened there, in case of this AC circuit, we are having the vectorical summation. So if you are going to add this value and this value, it is obvious that you are going to get this value. If you trust on me, you may try it out. Add this and this, you are going to get this. So this implies this plus this will be this one, obeying KCL. So we know IL and IC. Now once IL is known, so we had found number 1, then number 2. Once we are knowing IL, so what we can write, VR will be equal to IL into R2. So solving that, we are getting 46.42 minus J 51.72 volt. In polar form, it is going to be 69.5 angle minus 48.09 degree volt. So this is the RMS value of VR. And check out VL, that should be equal to IL into JXL. So that is coming to be 48.72 plus J 43.73 volt. If I am solving it out, you will be getting something like that, and that would be 65.47 angle 41.91 degree volt. So you could see that the RMS value of VL will be equal to 62.47. Now you can do one thing, you may add this and this. Once you are adding the two, you can clearly see that what you would be getting this one. And why it is so? Because if we are applying the KVL in this arrangement, what we can say that V2 should be equal to VR plus VL. Now it would be the vectorical addition. So therefore we are having this plus this should be equal to this one. So we can get. Now we had found this current and voltage, all the things we had found. Now coming to the next point, that is the active power, P. Now what is active power? That is VI cos phi. What is the RMS value of V? That is 200. What is the RMS value of I? It is 1.073. This one I had already computed. And what about the cosine angle? It is the angle between voltage and current. So the voltage will be lagging by minus 15 degree. The current will be lagging by minus 24.06 degree. So this 24.06 minus 15 degree will be the phase difference between the voltage and current. So that is coming to be 9.07 degree. So solving that, we are going to get the value of P is equal to 211.92 watt. Now what about Q? Q would be VI sin phi. This is the active power, this is the reactive power. So again we would be having all the values, so we would be putting it together. So what we are going to get is to be 33.83 var. The unit of this active power will be watt, this reactive power will have the unit of var, volt ampere reactive. This W stands for watt. And the apparent power S should be equal to VI, that is coming to be 214.6 VA. That you should be getting over here. VA stands for volt ampere. S is the apparent power. So active power, reactive power and apparent power we get found. Now if you want, you can prove that. If you want, you can easily prove that this S will be nothing but that is equal to square root of P square plus Q square. You can easily prove them. If you put all the values here, you can easily prove them. Now what we know, that the effective resistance, or I could say effective impedance of the entire section is basically ZXZ. So what is known to us? That ZXZ is equal to 184.1 plus J 29.38. So we can say it to be something called R equivalent plus J X equivalent. So therefore what we can write is that R equivalent should be equal to 184.1 ohm and X equivalent should be equal to 29.38 ohm. Now what is the current that is actually drawn from the system? That is 1.073. Now let us try to find out I square into R equivalent. So we are putting the value of I and R equivalent. We are going to get this value is coming to be 211.96. If you could observe, this value is almost equal to that of P, that is the active power. Now similarly, if I am going to find out I square X equivalent, then we would be finding it to be 33.83, that is exactly equal to the reactive power. And if I am trying to find out I square into ZXZ, the magnitude of the Z is already I had found 186.43. So if we are putting it over there, we are getting 214.64. That is approximately equal to the apparent power. So what it implies? This implies that this active power is basically the power dissipated in the resistive component of the circuit. Reactive power is the power dissipated, not dissipated I could say, the power stored in the reactive component of the circuit, and apparent power is the overall power consumed or stored. So that would be equal to the apparent power. So this is what the problem is, and I've personally found that if we would be proceeding in this way, it would be much easier for us to solve any problem related to the AC circuit. Hopefully you would find that thing useful and apply this information in the different circuit related to alternating currents. I am stopping here. Thank you. Have a nice day.